Okay, everybody, it's 3 o'clock. Welcome to the Department of Geography Colloquium Series for 2021. We have a speaker today that's joining us from the frozen tundra of Wisconsin, remotely. He's Ryan Good. He's a PhD candidate in geography at the University of Florida. He's a human geographer with training in geospatial analysis, remote sensing, conservation, and economic development. His research focuses on the relationship between environmental change, resource management, and economic development in the global South. Take it away, Ryan. Thank you for coming and give us a talk all the way from the tundra of Wisconsin.
Well, thanks so much, Dr. Fick. Let me get my screen shared before I forget that I need to do that. All right, Dr. Mullins already mentioned my background. If I can't be in Florida and I have to deal with the 11 inches of snow outside, I figured at least having the tropical background would be nice. This is my dissertation talk in fulfillment of that requirement. Those of you that have been around UF for a little while know the somewhat winding path I have taken to make it to this point. So I suppose I should thank the entire faculty for your support in one way or another through the years. But if you've heard me give research talks in the past, this may be somewhat different. That is a result of sort of two overlapping things. My interests have evolved and changed over time, and particularly once I joined Dr. Southworth's lab, did change direction somewhat. And additionally, this is much more focused on secondary data sources because COVID limited my ability to go back to the field and gather data following up on my preliminary trips to the field. So that is something that has helped to shape what you will be seeing today. My entire dissertation focuses on East Africa, defined here as the three countries of Kenya, Tanzania, and Uganda, as well as the African Great Lake, Lake Victoria, that is completely contained within those three countries. Broadly, the topical areas that my dissertation focuses on are issues related to land change science within the broader field of geography that we all work in. The study of human environment interactions across these national frontiers between Uganda, Tanzania, and Kenya provides, I think, a really exceptional opportunity to study the ways in which differing drivers of land cover and vegetation change from social, economic, political, and other human sorts of drivers all the way down to more natural drivers can all come together to impact social and ecological functioning, adaptation, and the resilience of the resultant vegetation and land cover that exists in that environment. So my research here is hoping to better understand the complex nature of these dynamics, as well as the drivers of vegetation and land cover changes. Particularly, I'm centered around climate, social, vegetation dynamics. So those are explored at multiple spatial and temporal scales in order to develop direct linkages between land cover and human drivers, also assessing change from a multinational, regional scale, all the way down in one chapter to a very localized study region in just part of the country of Tanzania. So therefore, it's my hope that this research is going to be relevant across many areas, from ecological analysis all the way over to a much more human focus on things like land use, policy, and management. All of that leads me to the frame that I'm using for this work that I'll be presenting to you today. And that's the frame that you see in the bottom bullet there of sustainability science. Sustainability science is an evolving area focusing on problem-centered, policy-relevant research, and the very nature of problems that are being confronted by sustainability research demands scientific inquiry that simultaneously considers social, economic, and environmental systems and addresses their present, and their future at the same time. Sustainable management of coupled socio-ecological systems tend to suffer from a pretty significant problem that these systems are just plain complicated, and that their behavior can be predicted by simply summing their individual components and understanding the cumulative effect. Instead, in the research that we'll talk about today, I argue that coupled socio-ecological systems are much more complex, composed of multiple dynamic and potentially stochastic components that are linked through numerous, sometimes unknown feedbacks that result in sometimes surprising emergent behaviors that cannot be predicted solely or exclusively from their individual components. Studying the three comparative regions of Uganda, Tanzania, and Kenya through this lens, and looking at their landscapes as a result of all these interacting factors will hopefully today lead us to an understanding of the nature of these complex relationships. So my broad methodological focus between chapters is one that is grounded in remote sensing. Remote sensing is one of the dominant tools used to evaluate land cover change, especially in conditions where fieldwork is limited, or in my case, completely prevented due to COVID. Remote sensing is incorporated in the analysis as it offers access to longer-term continuous data for larger extents than are traditionally used for ecological or social monitoring on the ground. This remote sensing methodology provides the means to expand vegetation studies from individual plots to landscapes to national or even multinational scales using high-resolution imagery that can bridge between fieldwork type data and coarser satellite scales, including things like the MODIS type products that I'll spend a little bit of time talking about today. So broadly for my dissertation, I have a few unifying research questions that have relevance to all of the smaller studies in each chapter. This research specifically tries to address three central challenges. The response of complex landscapes at a multinational scale to both human and natural drivers of vegetation cover and change, a more focused look at a specific case of Kenya and the importance of the driver of drought within this region for both agricultural and social security, and finally, a more focused look at one region on the Lake Victoria's shores where a dominant landscape conversion to urbanization can be assessed both in terms of land cover change and lake changes, addressing the larger implications of a local change when manifest at a more regional scale. The different analyses in different chapters depend on different geospatial technologies and modeling approaches that are incorporated into this research, usually built around the use of time series-based approaches within this framework that allow for a spatial recognition of these significant changes. This conceptualization and practice of these geospatial analysis tools will be of great import in the field of land change science and sustainability science and geography more broadly. So I'm going to talk about my chapters in a slightly different order than I just presented them. My initial research interests when I came to UF and initial years in the program were much more human focused and would have been much more human focused had I been able to do some complementary field work. But I'm very interested in the on the ground outcomes for local stakeholders in these environmental questions. So I'm going to start with the paper that focuses on the case study of Kenya because it is the most focused on those stakeholder outcomes. So this particular project studied the entire country of Kenya, which is composed of 47 distinct counties. All of my data analysis was done on that county level, and you can see the counties delineated on the map on the screen, and then highlighted with their drought status as of April 2019, according to Kenya's National Drought Management Authority's early warning bulletins. The counties that are marked in gray are not included in those bulletins because the NDMA does not classify them as arid or semi-arid and therefore not susceptible to drought. All of the other counties and in any of the other colors on this map are within the 80% of Kenya's land area that's classified as arid or semi-arid. The model that I'll be discussing as part of this work was trained using data from 2012 to 2014, but accurate rasters that inform my results were only created from January of 2016 through April of 2019. As for the community concerns that I'm hoping to address that I mentioned a few moments ago, Kenya is currently experiencing significant, ongoing, and likely to last into the future drought, with 5 counties classified in the alarm classification, the most serious classification level, behind emergency, which would essentially mean there is no water whatsoever. This means that environmental and production indicators in these counties and surrounding areas are notably outside of their seasonal norms. In addition, crop production is currently significantly below average for the 2nd season in a row, and it's likely that we're going to see at least a 3rd season of significant lows as well. This is not only a concern for feeding Kenya's population, but also for providing jobs for their workforce. About 26% of Kenya's gross domestic product is reliant on agriculture, but 70% of the Kenyan workforce is linked to agriculture in some way. This research is aimed at helping the 3.5 million food insecure people in Kenya, and about 1.6 million of those people are labeled by being in a crisis situation by the Kenyan government's Drought Management Authority. This means that those people have either large consumption gaps reflected by significant levels of malnutrition, or that they can marginally meet their food needs by depleting their other essential livelihood assets. So my research questions and objectives are overlapping here, so I'm going to talk about them together. The first objective of this project was to generate rasters that were derived from 10 different drought indices, including the combined drought indicator, the soil moisture deficit index, the standardized precipitation index, and the standardized runoff index. My hope coming into this project is that at least some of those tools would be useful to help local stakeholders monitor and understand drought, given the financial and technological limitations that they must operate under. The next objective for the project flowed directly from that, and that was to create a framework in order to compare the outputs of the model in those 10 different indices with the current data that's used by the Drought Management Authority that relies solely on vegetation health in order to better assist them and in turn local stakeholders, local farmers in understanding the information that can be gained from different drought indices. So as you can probably tell already in this project, I had some significant help and partners on the ground in Kenya, much more so once I was not able to travel to country. This research was specifically aimed at helping the end user of the National Drought Management Authority. This is an agency of the Kenyan government that works to ensure that drought does not end in emergency through monthly early warning bulletins that they prepare, and that this work is aiming to improve. As I previously mentioned, this work aimed to better these early warning bulletins that currently only rely on geospatial information derived from the Vegetation Condition Index, which is an index that is derived directly from NDVI data, meaning that it's only looking at vegetation greenness and vegetation health. So I wanted to be able to provide the NDMA with complementary data sources that could potentially make their bulletins more accurate. To meet these objectives, I collaborated with 2 additional organizations, NASA Servier and the RCMRD. NASA Servier is my domestic support partner. And they are a joint venture between NASA and USAID that provides satellite-based Earth monitoring and geospatial information to underdeveloped countries and stakeholders in those countries. The Regional Center for Mapping of Resources for Development, based in Kenya, is a severe partner in their Eastern and Southern Africa region that works across multiple countries and provides in-country support and coordination to on-the-ground partners. So this project used a variety of different satellites and sensors to gather a wide range of data. Those included the Soil Moisture Active Passive, or SMAP, L-band radiometer, both the Aqua and Terra MODIS sensors, and finally the Global Precipitation Management Dual Frequency Precipitation Radar, also abbreviated as GPM-DPR. In addition to these remote sensing data sources, I also used 3 ancillary data sets to complete this project. The first was land surface temperature data from INSEP. The second was precipitation data from CHIRPS. And finally, I gathered the drought classification data and vegetation condition index data from the historical records of what the NDMA has been producing in their monthly bulletins. All of this data was fed into and processed through an open source NASA published tool called the Regional Hydrologic Extremes Assessment System, or abbreviated as RHEIS. One of RHEIS's significant benefits is that it does not require the pre-processing of any data, no matter what resolutions it's at, no matter the spatial scale, the temporal scale, the spectral resolution. It will take any inputs, and as part of its processing, it will standardize the outputs to whatever you have set as your output. That makes it very user-friendly for people who are not technically competent or don't have a large amount of geospatial training. But as you might imagine, it does make it a very computationally intensive tool. So this project's methodology followed 4 main steps. The first was the acquisition of data. RHEIS is a model that runs solely in Linux. So using RHEIS in Linux, I ingested data from all of those data sources that I ran through beginning in 2012 and running through the most recent data that was available, including soil moisture, land surface temperature, and precipitation data from all of those sensors and complementary sources. The next step was to process the data. This was the most intensive step of the methodology. I did this using the variable infiltration capacity model that operates within RHEIS. The VIC model, or VIC model, is a large-scale hydrologic model that utilizes land surface models in conjunction with meteorological drivers to produce output pixels that show whatever indices the user tells the model to calculate. For this project, the output pixels were limited to a 25-kilometer resolution due to the computational limitations of RHEIS's computational demands. As I mentioned, RHEIS standardizes all of the data that's fed into it, which is really one of the great benefits of the model. It can take data from all those different sources and resolutions to create standardized outputs. The user doesn't even have to understand the different types of resolutions that data can exist in, as long as they have sufficient data to address the output they're trying to create. As part of the processing through RHEIS, the data is saved into a post-GIS database in which code has to be run to generate the drought indices. The drought indices were created by this model for Kenya. Were 10 different indices, including the standardized precipitation index and the standardized runoff index, both of those for 1, 3, 6, and 12-month accumulation periods. That's how far back in time it's looking, as well as the combined drought indicator and the soil moisture deficit index. Data was calculated for each index once a day from January 1st, 2014 to April 30th, 2019. This work also standardized the NDMA's VCI data in order to allow better comparisons for our indices by calculating a z-score for each value. I then moved on to my data analysis, which I started by creating a time series for each of the indices for each of Kenya's 47 counties. I then used pandas in Python to create a Pearson correlation coefficient and covariance between the calculated indices to see how they compared to one another. That standardized VCI data was also included in the correlation calculations to compare against their current information. Finally, from this data, I created my end products, which were a drought time series, the RIAS drought indices themselves, and the evaluations of them. So the results were composed of 10 different drought indices, which I've already listed for you. I'm not going to make you listen to them again, for each of Kenya's 47 counties for each day from January 1st, 2014 through April 30th, 2019. If you're doing the math at home, that's about 743,000 total data points just for the CHIRPS precipitation data. And I also ran the model using the GPM DPR precipitation data, which effectively doubles the amount of data points. So this was very much a big data project. I obviously cannot show you all of those data points, which is why I've had this fun little animation playing. This is the calculated index for January 1st, 2019 for each of the labeled indices that you see. Just a quick snapshot of the data that was created. So again, here on the left, we have the RIAS results. And then for the sake of comparison, on the right is the VCI, which is the NDMA's current measure coming solely from vegetation health. Because there's so much data that we're working with here, it's not reasonable to try and analyze or present all of it today. So I picked 5 case study counties. They were selected to try and ensure geographic and hydrologic diversity. There were 2 that were selected, Wajir and Isiolo counties that are labeled I and W on the map that regularly experience drought. 2 that rarely experience drought, but are still classified as arid or semi-arid. Those were Narok and Kwale counties, the N and the K on the map. And then 1 somewhat control county in the middle that was the closest to the median that I could find, which is Mandera County in the extreme northeast labeled with the M. So I calculated time series for each county. If we look at one of our case study counties, Isiolo County, you can generate time series to see how the indices compare to one another. These are the 4 SPI indices over time from 2014 through 2019. The nuance of this variation is not terribly important to dive into today, but these are 4 variations of the same index that are measuring the exact same thing just over different periods of time. So you can see very quickly from that alone that the time period you're looking at plays a large measure in what value you are presented as far as drought. The same thing is true of the runoff index, which also has the 4 accumulation periods. Perhaps more interesting, comparing the other 3 indices, the combined drought indicator, the soil moisture deficit index, along with the vegetation condition index that the Drought Management Authority was already using. If you look at this case study time series from Isiolo County, the first thing that jumps out is the VCI, represented in yellow. Doesn't look much like the others. We discovered midway through this project that for several counties, the NDMA had actually miscalculated. That index should not go negative in that way, illustrated by the other 2 having positive values in that same time. So that alone was a meaningful result for them, just to point out that there had been that notable issue. For a more scientific understanding and comparison of what's going on, a little more quantitatively than just these visual time series, I wanted to see how they compared. So I made a heat map of how they compared for each county. This does not include the combined drought indicator because it's categorical, not continuous, so it can't fairly be compared. As you can see in the results here, the SPI and the SRI are very highly correlated to one another. So moving forward, when trying to use any of these tools to predict drought, choosing one of those would be more than sufficient for most end users on the ground. In addition, the SPI and SRI indices with 1 month accumulation periods were the only outputs of this model that had negative correlations with the pre-existing VCI data, making them notable outliers in comparison to all of the other indices here. While I've only shown you the visual results for Osceola County, all of the case study counties had very similar results. Sorry. Diving a little bit deeper into them, SPI1 and SRI1 are such outliers because they're looking exclusively at the short-term changes that exist on a 1 month running basis, and they're directly influenced by any individual rain event. This means that these indices are really, really good at looking at surface soil moisture, but they're not immediately comparable to longer term indices such as the 12-month accumulations of either, which is what you see pictured on the right here compared to the 1 month on the left. The current tool that the NDMA uses, the VCI index, relies solely on vegetation health indicators, which have a significant time lag in displaying the impacts of rain or drought events. Vegetation takes time to green after it rains, it takes time to brown after it stops raining. So in contrast, SPI1 and SRI1 visualize rain events independent of vegetation growth, and therefore could be effective tools in an early warning forecasting system for understanding drought. The longer term indices, such as the 12-month accumulation that you see cycling on the right, are more illustrative of water table health and accumulation and change over time. The differences as it cycles through time here are pretty stark for any individual date. Contrasting with that, the combined drought indicator is a categorical index that has five possible results. 0 means there is no drought present. 1 means there's a precipitation deficit. 2 means there's a soil moisture deficit. 3 is vegetation stress following a precipitation deficit. And 4 is full vegetation stress following precipitation or soil moisture deficit. At the beginning of this project, I thought that the CDI was going to be the most useful index because of the very simplistic results in this categorical classification. Additionally, it takes precipitation and soil moisture deficit as well as vegetation stress into account. However, as you saw in that cycle, for the data that we were able to analyze, it didn't return very interesting or complex results. The index never went higher than 3, even though we know some of these regions are experiencing exceptionally bad drought. And at many times, such as this snapshot from May 1st of 2019, it returned universal results of 0. This would suggest that moving forward, CDI could potentially be useful if the thresholds that are used to calculate the different categories were somewhat adjusted within the data, but that would require some tinkering that I have not had a chance to do at this stage. So with all of this data, I was able to reach a few broad conclusions from this project. The first was that the drought indices that take into account longer periods of time, such as the SPI or SRI 12-month accumulation periods, seem to be strongly linked to groundwater table health over solely precipitation-related events. The SPI and SRI 1 and 3-month accumulations are much more closely linked to immediate and surface level precipitation and soil moisture health. SPI1 and SRI1, therefore, have very high potential for use in a short-term forecasting system in this environment. In addition, I concluded that the Vegetation Condition Index currently used by the Drought Management Authority is comparatively limited in inferring drought status due to its inability to effectively measure short-term changes in drought conditions because it is limited by that vegetation lag. It does not pick up on short-lived drought events or the immediate end of drought events. Finally, the Soil Moisture Deficit Index, or SMDI, I haven't really discussed much in the results, but I do think that it is probably the most practical all-purpose index because it operates entirely independent of plant health, avoiding that vegetation lag that's such a problem with the VCI. This is particularly important in Kenya because the country is prone to invasive species that can stay green longer than naturally occurring vegetation, making any VCI data potentially inaccurate for plants that are actually relied on as food sources by the Kenyan people. There were a few limitations that I should acknowledge of this project. The most notable of which is that it was only able to run at a 25-kilometer resolution, which is a very large pixel size. The NDMA itself evaluates drought risk on a ward level within individual counties, and wards are much smaller than 25 kilometers in some cases. So ideally, this model would run at a smaller 5-kilometer resolution. Another limitation faced during this project is that I was unable to run the assimilation that I had hoped for, as it hadn't been programmed yet by the people creating the RIAS system. The assimilation function within RIAS uses observations from SMAP or soil moisture ocean salinity, or SMOS, on a weekly level to back check the model's calculations and ensure that they are correct. Once this functionality is added by NASA, this is something I'm going to come back and do to double check the accuracy of my results. These limitations bring us to the future work of where this will go moving forward to become hopefully more useful for people on the ground. This includes running the model at the 5-kilometer resolution that I mentioned, as well as trying to aid the NDMA into incorporating more useful geospatial analysis into their early warning bulletins. Additionally, everything that you've seen today was run in the model using a nowcast mode, meaning the model could only calculate values for days that actually had data from the sensors. In the future, it will hopefully begin allowing a forecast function as well, allowing the model to project drought conditions into the future. So moving on to my second paper, we're going to zoom back out and look at a larger scale now across all 3 of the countries and consider vegetation persistence. Again, the 3 countries I'm examining for this are Kenya, along with Tanzania and Uganda. Before we consider anything else, we should understand that in this region, even though it is completely contiguous, there is significant environmental variation. Uganda's agroecological zones are in particular much more humid, while as Tanzania and especially Kenya are notably more arid. So this research looks specifically at the use of vegetation persistence as a variable of interest. Over time, interest in the human impact on natural environment has increased pretty dramatically. It's something that a lot of us make our living off of every day. But in the last few years, while it has become much more of interest, Repeat digital synoptic measures of the Earth's surface have stimulated many land change science research questions designed to improve our understanding of the human environment interactions. Satellite remote sensing is ideal for this task, providing consistent, repeatable measurements across a suite of spatial scales, and it's well suited to capture the processes of land surface change, such as human activity, fire, floods, and so on. Detection and characterization of such changes is often the first step in understanding the mechanisms and identifying their drivers. Directional persistence is a measure of the cumulative direction of change over a time series relative to a first observation. Cumulative frequency can be used to determine the critical values of persistence corresponding to upper and lower desired significance levels. The smallest value of persistence is one which equals or is less than the generally used levels of significance and can be extracted from a simulated frequency of directional persistence generated under conditions of the null hypothesis that values the indices, such as NDVI in this case, which are independently and normally distributed. The greater the absolute value of the preceding NDVI, the less likely a series is to continue in that direction, be it increasing or decreasing. These approaches for examining vegetation change are conducted in a spatially explicit manner and will further our understandings of the impact of climate variability, policy, and institutional change on the landscape by supporting identification of sites within the study area that are experiencing critical changes in vegetation now and back across the preceding 20 years. So my research questions in this, centered around this vegetation persistence idea, are twofold. I examined what patterns can be observed in directional vegetation persistence throughout the 3 East African countries during the last 20 years in the 21st century. And additionally, I was interested within each state how it varied nationally. I was also curious to find what drivers are impacting this persistence, if it's driven solely by precipitation, if there's any import from protected areas and national parks, if there's any evidence related to land transactions that have become very common in this part of the world. So this vegetation change analysis was conducted based on a time series analyses of NDVI seasonal composites. Central to the analysis was a statistical metric called directional persistence, which is used to detect vegetation gain, loss, or no change at a pixel level using time series NDVI observations. To calculate directional persistence for a pixel, first, its initial benchmark NDVI value is established based on its average NDVI value from the years 2000 to 2004. The 5-year average from this period was used to obtain robust and defined benchmark values for every pixel in the study area. Then those pixels NDVI values for the subsequent 15 years following the benchmark period were compared to the benchmark value to identify the number of years with observed NDVIs larger or smaller than the benchmark value. The persistence metric value, D, counts the difference between the number of years with NDVI observations larger and smaller than the benchmark. Thus, the persistence value of a pixel was calculated using the equation you see there on the screen. The persistence values are calculated independently on a pixel and season level, and this results in 4 different persistence products, one corresponding to each of the 4 boreal seasons through the year. So when we look at the broad results of what persistence looks like in this study area, perhaps the most notable result is the December, January, February season, the North American winter, which is the set of columns on the far right side of this graph. The overall trend of negative persistence and localized strong negative values during this season really stands out, as this season immediately follows the short rain wet season in November and December. Vegetation trends that are driven solely by climate would be expected to have a more positive level of persistence through the last 15 years of observations. And this would seem to support the hypothesis that multiple drivers are influencing this land cover beyond solely climate. Moving forward in time and to the far left of my graph, the March, April, May season, while less extreme in its results, supports the idea that climate is not the sole driver as well. This is one of the drier times of the year, yet for the study period, the overall trend was less negative than the preceding wet season in the December, January, February period. The June, July, August season contains the largest wet rains of the year, which is supported by the wider positive trends observed during this time of year. Based solely on this season, climate would appear to be a more significant driver compared with the other seasons, and it appears the large amount of precipitation during this season overwhelms the influence of other drivers and coordinates with them to result in a more positive, persistent pattern. Finally, the September, October, November season fits as a reasonable in-between period of the more extreme June, July, August, and December, January, February observations as the wet season rains in the North American summer stop and other drivers become more influential on the overall system. Interestingly, the negative trends observed during this time persist into the December, January, February season, as I already mentioned, despite the reoccurrence of the second wet season. So if we look at things on a more individual level, country by country, we can see trends that line up with the different environmental patterns present in the country. Most notably, Uganda on the far right of this graph exhibits notably positive trends of persistence in 3 of the 4 seasons. But even in Uganda, with humid climates and significantly larger amounts of precipitation, the December, January, February season has a slightly higher incidence of negative persistence than it does positive. Kenya and Tanzania, both with significantly more arid environments, have more significantly negative precipitation throughout the seasons, most significantly highlighted in both countries, again, in the December, January, February season. I know this graph is a bit much to look at. I'm fitting a lot of variables and a lot of observations onto one screen. It perhaps is easier to digest if we look at it spatially. So if we start in the December, January, February quarter, the region broadly experiences negative vegetation persistence in this time, with only a few small parts of the study area registering positive persistence. When we move on to March, April, May, this season shows significantly less negative persistence, particularly in Tanzania. The southern portions of Tanzania are notably more positive during this season. This trend continues into June, July, August, where there's a more broad positive trend as the countries come out of that long rains wet season. Finally, in September, October, November season, there's a notable split in the region, with much of the northern areas showing high persistence levels, while the southern portions, particularly near the Indian Ocean coast, show notable negative levels of persistence. Even at a national level, though, we see a lot of variation. So quickly looking at just a few case study examples from within the countries perhaps reveals the impact of some other things. This is the site of a land transaction from central Tanzania. On the left, we have the ground as it looked in 2000. On the right, the ground as it looked in 2020. And you can see the clear change that has happened during the land transaction, as well as the impact that that observably had on vegetation persistence during those years. There's not enough evidence here to posit causation, but there's certainly a correlation. Other interesting factors are happening in and around Lake Victoria, particularly in this study area from southern Lake Victoria and northern Tanzania. I'm not sure how well it's coming across on the screen, but the period from 2020, the picture that's labeled B, there's notably visibly more vegetation, greenness in the water than there is 20 years prior. So much so that it's being picked up by NDVI calculations and therefore is being impacted on this persistence metric. And you see in the visualization of persistence that even large portions of the lake are registering mildly positive or mildly negative vegetation persistence, despite the fact that it's open water. It's important to remember that vegetation persistence does not mean greenness. This doesn't mean that there is greening or browning occurring. This simply means that there is the consistent presence of vegetation greenness or a decrease in vegetation greenness over the study period. As an example, this is just to the east of Lake Turkana near the Kenya-Uganda border. And this is one of the more arid places on Earth. As you can see from the true color visualizations, there's very, very, very little vegetation present here, but there is consistently positive directional persistence occurring. Finally, sometimes there's not a lot of visual change, such as from this imagery around the Serengeti and Mount Kilimanjaro National Parks, but there is observable, quantifiable persistence in this case with pockets of both negative and positive persistence. This is particularly interesting because one of the variables that I hypothesized would potentially be playing a role in the presence or lack of vegetation persistence was the impact of protected areas and national parks. So this is a map of where all of the land that is protected in some form in East Africa occurs. And if we look at the persistence graph, it looks much more centralized than the original one did. Just for the sake of comparison, there's the original one in the corner. There's notably less difference between negative and positive, even in the December, January, February. And in other seasons, there's much more positive persistence than there is negative persistence. This trend holds when we look at individual country levels. I apologize for burning through this a bit quickly. I know I'm running short on time. So skipping to the conclusions we can draw from all of those graphs, the national boundaries very clearly seem to have an impact on vegetation persistence in this region, which highlights the importance of policy, not just environmental change. It seems clear that climate does play a role, but is not the sole driver, which again emphasizes the importance of human management and policy and understanding vegetation and environmental health. The region as a whole is experiencing negative directional persistence, although Uganda is much more oriented towards positive persistence. Those protected areas have notably more positive persistence, particularly in Tanzania, where roughly 1/3 of the land surface area is protected. This would indicate the success of protected areas in maintaining or improving vegetative cover. And finally, other variables such as land transactions and urbanization are potentially playing a role here and would be good avenues for future research to focus on. The third paper of my dissertation, I'm not going to talk about really much at all because I'm out of time, but it is looking at land cover change in northern Tanzania near the coast of Lake Victoria. It's marked on the map here where it's looking. Lake Victoria, if you don't know, is the world's second largest freshwater lake and is a significant force acting on all three countries bordering it. It has a complex relationship with areas, particularly those near the coast. So this paper is seeking to understand what kind of land cover change occurs in northern Tanzania and how we can model and visualize that change using a combination of methods such as NDVI change analysis, random forest classifications, and Google Earth high resolution imagery to determine change. Just as one quick result, we can see that looking at NDVI, the signature is picking up greenness in the lake, which supports what we saw in the previous paper with the visible greenness in parts of Lake Victoria. The findings of this paper conclude that rapid urbanization is very evident on the landscape level as changing land cover patterns are observed. And overall greenness is increasing, but some of this is changes in the lake itself, such as in that image you can see where there's complete vegetative cover on the surface of the lake. Whew. I apologize for running a bit over on time, but I would be happy to take any questions about any of this research that anyone has.
Okay, let's open it up for questions. Anybody out there?
I have a question. Do you have a reaction?
Sorry,
Hello?
Dr. Fick, I don't know exactly how to manage this. I can't tell who's talking because I'm still in full screen.
Cynthia Simmons has a question.
I do.
Yes, Dr.
So-
Simmons, yes.
The last paper you were talking about, it was interesting looking at the impact that national boundaries had, and you brought up the policy aspect. But what about the economic aspect, or the location access to cities and other, which I think would have, could have explained quite a bit as well.
Yeah, I think that there's definitely some validity to that. That is not something that I've examined very, very deeply at this point, but particularly getting within national borders and looking at more singular national level scales, I think that would be right at the top of the list of questions to ask for that analysis.
Yeah. I think even for a statistical analysis, there's enough scholarship out there about the implications. So I know, for example, heading from Ohio into Michigan, you're right near Toledo, but once you cross the border over into Michigan, all of a sudden you're there with, grassy areas, and even the other side is suburban neighborhoods. And so part of it has to do with the taxes, but it also has to do with, access to markets and what, going back to a von Thunen type of a look at that implication, maybe something you want to add to your analysis. And it may be something on the human geography side, economic geography side, trying to understand the drivers that you should at the very least be controlling for. Access to market, distance to cities, type of a thing.
Yeah, that's a very good note.
But I enjoyed your talk, and I really like your background.
Thank you. And I've seen that people are raising their hands digitally, and I'm not seasoned enough at Zoom to know how to find who is doing that to ask questions.
Who's next? Who is interested in asking a question?
I have a question. Thank you, Ryan. This was really interesting. And in your second paper, you mentioned both protected areas and land transactions possibly having an impact. And I know it's kind of fairly on, and this might be more of a hunch, but do you have an idea if you think protected areas or land transactions have a bigger impact on vegetation persistence?
Yeah, with the caveat that I haven't gotten a lot of land transaction data yet, because it's not as centralized as protected areas. I think that based on the analysis I've done at this point, it's definitely protected areas, which for those of us that work or have worked in conservation should, I hope, be at least mildly reassuring that it does appear based on the evidence from these three countries that the protected areas are doing their job, assuming that at least one of the goals was to maintain cover and protect vegetation to some degree.
Okay, any other questions?
I have a question. Great job, Ryan. Super interesting. See what you've done. I was curious about the drought analysis, the Kenya paper for drought, and I think your analysis was 2016 to 2019. And I was just wondering why this time period and why you stopped in 2019, April of 2019. Just curious if you could explain that, the reasoning there.
It doesn't go any earlier because a lot of the data sources are not available any earlier than that. And the model requires 2 years of training, which is why there's a bit of a lag from when the data started to when the results started. They only go through 2019 because I thought it was very important to be able to compare results against the data that was created and published by the Drought Management Authority, because a large portion of the project's goals were to go back to them and inform them and work with them. And they have a significant lag on when they archive and publish things beyond their on paper only monthly bulletins. And they are about a year behind time right now. So through mid 2019 was about the quickest that it was, or the latest that it was possible to get data from them. So that's the latest that I did the analysis for as well.
I see, thanks. That makes sense.
I have a question, Brian. On your first paper, you were doing correlation analyses and you're looking at the correlation of these indices. Did you consider perhaps looking at pairs of indices and running correlograms? So you look at the correlations in terms of lags or leads. So you basically, you were looking at the same time period, the correlations, but sometimes you might get some insights as to the correlation of indices either in leads or lags, if you know what I'm saying, and put a correlogram together, series of values.
Yeah,
you might want to do that for a selected couple of pairs of values, because sometimes your higher correlations might be a lag of 1 or lag of 2 or a lead of 1 or lead of 2. And you may gain some insights on the relationship between these indices based on that. So just a suggestion.
Yeah, that's an excellent idea, Dr. Fick. I'm a bit embarrassed that did not occur to me, but that's a very good idea.
Open the floor. The floor is open for questions. Okay, we're past the period length here. It's 3:55 now. I know a lot of people have to run. A lot of people have to go. For those who are going to stick around, please do so if you have a question that you still might want to ask Ryan. Ryan, thank you very much. It was an interesting presentation, and this is really important work, and trying to understand vegetation persistence, particularly, how much of impact is coming from, like Cynthia's interest in economics, from policy and all this other stuff, and then climate change. Very interesting stuff. So thank you for an interesting presentation.
Yeah, thank you, Dr. Fick, and thank you everyone for coming and hearing about my work.